Hey there, welcome back to Abstract Algebra. Today we're going to be looking at a topic from section 2.9 in our text, direct products. So I've got the goals of the lecture written there for you to see. There's sort of three things I want to get done with you guys in this video lecture. I want to introduce the notion of direct product of a collection of groups. Our collection will primarily just have two groups in it, but we can write down some things for arbitrary collections. Then discuss some properties of these things. That discussion is mainly going to be me pointing out properties. I'm not going to really be proving many of those things. They're going to end up being in your homework sets. So you're going to be proving these properties, but we'll talk about them here together in the video. And then we're going to end the lecture with specifically talking about cyclic groups and trying to understand a condition under which the direct product of cyclic groups is cyclic. All right. So we'll get going here today. What is the direct product of let's say, two groups? Let's say we have two groups, G1, G2, are groups. Well, in Math 240, you learned what I mean by the direct product, or sometimes people call it the Cartesian product as a set. It's written like this. You pronounce it G1 cross G2 or G1 times G2. And what is it? Well, it's just the set of ordered pairs, things that look like A comma B, and they're ordered in the sense that the thing you write first comes from the first factor. In our case, that's G1. The thing you write second comes from the second factor. In our case, that's G2. So that's the Cartesian product of the two sets, G1 and G2. And then what I'd like to do is I'd like to make that into a group. There's a very natural operation on G1 cross G2. If we take two elements of it, I'm just going to kind of quantify them out loud here. If I took, say, an A1, B1, and an A2, B2, so it's implicit in my notation there that A1 and A2 come from the group G1, B1 and B2 come from the group G2. There's a very natural product on these things where we'd multiply these two pairs by saying, well, multiply A1 and A2 in the first coordinate. That makes sense because that's an element of G1. And then multiply B1 and B2 in the second coordinate. That makes sense because that's an element of G2. All right, so this thing, let me give it a name. We can refer to it later. Just call it the binary operation defined by star. And it's certainly a binary operation. You know, given two ordered pairs, I've produced an ordered pair. Cool. That binary operation, it's probably not too surprising, gives G1 and G2 the structure, or sorry, G1 cross G2 the structure of a group. And that group is called the product group. So here I've stated it as a theorem. You can already see that I'm not going to prove this theorem. I'm going to leave it as an exercise to you. But what the theorem says, if you take two groups, then this Cartesian product, G1 cross G2, is also a group. So that's the main part of the theorem, is that this thing is a group under the operation defined by that equation that we called star up there. And then, well, what would the identity element be? The identity element would be the ordered pair consisting of the two identities. So I'm just writing E1 and E2 to denote the identity in G1 and G2. And then the inverse of an element, AB, well, it's just the ordered pair of inverses. All right, so that's going to end up being one of your problems to prove in homework 8, that this binary operation makes G1 cross G2 a group. And the proof will go smoothly because, again, G1 and G2 are proofs, are groups where all of those properties hold. A couple of remarks here. They look a little messy, but I'm just going to scroll down to them. The first remark is that we don't really just have to do this with two groups. If you take any, in this course, we'll keep it finite. If you take an infinite number of groups, this notion gets mildly more complicated. But if you take any finite number of groups, then maybe in Math 240, you know, the Cartesian product of a finite number of sets is just the set of ordered, well, I can't call them pairs, I usually call them ordered n-tuples. So the idea is that the element in the ith slot comes from the ith group. And in the exact same way that you could prove, in fact, if you want in your exercise, you could prove this for any n greater than or equal to 2, that the Cartesian product of a finite collection of groups is a group, the identity is the n-tuple of identities, and the inverse of an element is the n-tuple of the inverses. So really the fact that we have two factors is not that big of a deal. It's just notationally a little bit easier to write down. A second remark is that if we're writing things additively, if the groups are written additively, then we write the Cartesian product additively as well. So I'd still write ordered pairs, A1, B1, A2, B2, but I'll add them together if the groups are written additively, and then that addition takes place in the coordinates. In both cases, we call this coordinate-wise, well, multiplication coordinate-wise addition, and it makes the Cartesian product into a group. All right, let's look at an example. First example I wanted to choose, maybe it's going to look sort of familiar to you. I'm going to take G1 and G2 to both be the real numbers. And remember, when we write that, because they're not non-zero real numbers, I mean the real numbers under addition. Then the Cartesian product, R cross R, which a lot of times just gets shorthand denoted by R squared. It looks like it's good notation. What is it? It's just the set of ordered pairs, X and Y. X and Y are real numbers, and we add those ordered pairs like that. We add the X coordinates and add the Y coordinates. So you recognize that from Calc 3 or maybe from your linear algebra class. That's just vector addition in the XY plane. So the vector addition in the XY plane is really just the sort of group structure of the Cartesian product of R with itself. Or if you've had the advanced calculus class, higher level linear algebra classes, you can take any number of coordinates. If you take the direct product of the real numbers with itself n times, then you get the Euclidean n space. And the group operation in there is just adding coordinate-wise. So the identity in your linear algebra class, you usually called that the zero vector. It's the n tuple consisting of all zeros and so on. Cool. All right, so some properties of direct products. Let me just put all three of them there where you can see them. Again, I'm going to leave all of these things as exercises for you. I'll type some of them up, select some of them from the book, and they'll appear on your 8th homework, which I'm not looking at a calendar, but I think it'll be due on April 10th. So what are some of these these properties of direct products? Well, the first one, I didn't quantify all of this, so we're being a little bit informal, but I'm here to kind of talk you through it. The first one says that the direct product doesn't depend on the order. The product of G1 and G2 and the product of G2 and G1, well, they're not equal as groups, but they are isomorphic. And if you like that business with more factors, you can permute the factors in a direct product any way you like, and you're not going to change the group structure of the direct product. Change the set, but not the structure. A second one, if both G1 and G2 are finite, then so is the direct product. And in fact, there's a very nice formula for its order. The order of the product is the product of the orders. Sounds kind of nice. So if you take a group with 5 elements and you take its direct product with a group with 10 elements, then you're going to get a group with 50 elements in it. They multiply. It's going to be one of your exercises. Third one, if both the factors are abelian, then the direct product will be abelian. So the product of abelian groups is abelian, is that third thing. So these will all show up in your homework. And how you're going to do it? Well, you have to do it directly from definition. You don't really have much beyond what is the definition of the direct product of two groups. It's a group structure on the set of all ordered pairs that uses this binary operation. So those exercises should follow from that. You don't have any other machinery. Let's do some examples. Kind of got just a skeleton here, and I'll write as we go. But the first example I wanted to look at was the direct product of the cyclic group of order 2 with the cyclic group of order 3, or among friends, Z2 cross Z3. So I have a question for you, and you can pause this video if you want to think about it before I just blurt out the answer. But my first question is, what's the order of that group? We were just looking at a property up here. It said that if you have two groups that are both finite, then the order of the product is the product of the orders. Okay, well, Z2 and Z3 are both finite. So the order of Z2 cross Z3, have you already computed it? It should be the order of Z2, that's 2, times the order of Z3, that's 3, that's 6. So Z2 cross Z3 is a group of order 6. Yeah, Z2 and Z3 are both abelian, the property that you're going to prove in your homework. We know that Z2 cross Z3, it's an abelian group of order 6. All right, so we know some things about that. Let's play around in it. Let's get a feel for what it's like to compute in a direct product. Um, I'm writing the ordered pairs like this. So I'm choosing 1, comma 1, and I'm not writing the brackets. I'm just going to write numbers. And you have to be a little bit careful here because this 1 that I'm writing on the left in that ordered pair, that represents the element 1 in Z2. So for example, 1 plus 1 is 0 in that first coordinate. The 1 in the second one represents the 1 in Z3. How do I know that? Because they're ordered pairs from Z2 cross Z3. So in that second coordinate, 1 plus 1 is not 0. 1 plus 1 is 2. Yeah, so you have to be a little bit careful. I'm kind of abusing notation a little bit and leaving a lot to context. Okay, good. But what do these outer parentheses mean? Well, that's just cyclic subgroup generating notation. So it doesn't look all that nice when the element itself is written as an ordered pair, but we'll have to get over it. So determine the subgroup. Well, we do this all the time. We do this all the time. Well, how do you determine a subgroup? You grab your element and you start adding it to itself. So you know that element is going to be in the subgroup. Well, what's it going to be when I add it to itself? Well, in the first coordinate, I add 1 and 1, and I add 1 and 1 in the second coordinate. But like we were just saying, in the first coordinate, 1 plus 1 is 0. In the second coordinate, it's 2. All right. So maybe where to start writing down this subgroup. Let's start listing its elements. Maybe I can, if I write nicely, I can fit them in here. So we know we certainly have the generator itself. We just picked up the element 0, 2. And so now I should take the element 0, 2 and add 1, 1 to it. Okay, well, that's going to be 0 plus 1, comma 2 plus 1. And simplifying, if you like, quote unquote, that's 1, comma 0, right? 2 plus 1 is 0 in Z3. So we've picked up a third element. It's not the identity, so we better keep going. What's the identity? Can you pause it before I say it? The identity in the group Z2 cross Z3 is identity, comma identity. So we're looking for 0, comma 0. We're looking for 0, comma 0. All right. Let's keep going here. We got 1, 0 was our last output. I'm adding the 0.1, 1 again. What are we going to get? 1 plus 1. We're going to get 0 plus 1 in the second coordinate. That's 0, comma 1. 0, comma 1 goes in there. Okay. Add 1, 1 again. I'm going to skip the intermediate step this time and write that that's going to be 1, comma 2. So 1, comma 2 just made it in there. Take 1, comma 2 and add our 1, 1, and you get 1 plus 1, that's 0. You get 2 plus 1, that's 0. That's the identity. It's over. The identity is the last element. I'm sorry, I have to kind of squeeze it in here. Yeah. And if you count them up, that's 1, 2, 3, 4, 5, 6. That's the whole group. So the subgroup generated by 1, 1 turns out to be everything. Z2 cross Z3. Cool. So that element 1, 1 generated the whole group. I would encourage you, while you're first kind of thinking about these things, there are 5 other elements in this group. We took the subgroup generated by 1, 1. There are 5 others. 0, 2, 1, 0, 0, 1, 1, 2, 0, 0. I'd generate the subgroup by all of those things, just to give yourself some practice computing in this. Yeah. So we found an element that generates the whole group. What kind of group does that make? Z2 cross Z3 makes it a cyclic group. Makes it a cyclic group. We already said its order. Its order is 6. So here's a question I keep asking you over and over. Can you pause and answer it? If I have a cyclic group of order 6, what's it isomorphic to? Yeah, every group, cyclic group of order 6 is isomorphic to Z sub 6. So Z2 cross Z3 is isomorphic to Z6. And what's an isomorphism? Well, the generator 1, 1 could correspond to the element 1 in Z6, for example. Cool. Let's do it again. Another kind of example template ready for us here. I don't want to reveal that down there. Same questions. Same questions about Z2 cross Z4. So what were those questions? Well, the first one was its order. Have you said it already? The order of Z2 cross Z4 is 2 times 4. It's equal to 8. Z2 cross Z4 has 8 elements. It makes sense. Elements of Z2 cross Z4 look like A comma B. A comes from Z2. You have 2 choices for that. It can be a 0 or a 1. B comes from Z4. You have 4 choices for that. Yeah. So you have 2 choices for A, 4 choices for B. You have 2 times 4, 8 choices total. Nice. All right, so it has order 8. Let's generate the subgroup generated by 1, 1 again. Subgroup generated by 1, 1. So here, we'll do the same kind of methodology, but we kind of pick up the pace this time. It's got 1, 1. It's got 1, 1 plus itself. That should be what? 0, 2. If you take 0, 2 and add 1, 1, you get 1, 3. Take 1, 3 and add 1, 1, you get 0, 0. So it's over. Sorry about that. I guess I don't have to list them in order, but I'm just being a little finicky here. We got 0, 2 next. We got 1, 3. Then we got our identity. So it's over. Subgroup has order 4. 1, 1 has order 4. So it didn't generate. All right, that doesn't mean some other element doesn't generate, but 1, 1 didn't generate. But if you think about it, actually, what if we did take some other elements? Just switch color here so it's easier to focus on. What if I wanted the element generated by, say, AB? Okay, well, it's got AB in it. When I add AB to itself, I'm going to get 2A, 2B. But in Z2, no matter what A is, 2A is 0. Yeah. So then I add AB to that, and well, 0 plus A is A, 2B plus B is 3B. And then I add AB to that, and I'm going to get A plus A, well, that's 0, and I'm going to get 4B. And in Z4, no matter what B is, so actually, any element AB, if you take the subgroup generated by it and look at how many things are in it, we just proved you're never going to get more than 4. You're going to get 0, 0 when you add anything to itself in this group 4 times, because 4 times will 0 out the first coordinate, and it's every other time is going to 0 out the second coordinate. Or, excuse me, the 4 times will 0 out the second coordinate. Every other time zeroes out the first. Yeah. So I think we just gave ourselves a proof that Z2 cross Z4 is not cyclic. Maybe you're surprised. How do I know it's not cyclic? Well, I know that because I just proved that any element's order can be at most 4, but this group has order 8. If it were a cyclic group, we'd have to have an element of order 8. And we're not going to find one. Nice. All right, so the last thing I want to do in this lecture, trying to keep it tight and focused. I know that I'm talking fast, but hopefully you can pause it and think and kind of go back and think. I want to prove that what we just saw is actually kind of an illustration of a fact that's true in general. This first example that we did, Z2 cross Z3, it ended up being cyclic. Maybe I should do it down here. It was because 2 and 3 don't have any common factors. I mean, roughly speaking, this is kind of the proof that the first number that is a multiple of both 2 and 3 is 6. So we weren't going to zero out in both coordinates until we had done it 6 times, and 6 is the order of the group. The second example, to say kind of what happened, there is a number that is a multiple of both 2 and 4 that's smaller than 2 times 4. And that number is 4. And because of that, everything pooped out before we could possibly get up to the order of the group. So we're not going to have a cyclic group. All right, so those are sort of fuzzy, but not far off from the proof of what this next theorem is. I'm going to kind of try to hide the proof for you for a second, but what I want to try to prove to you is what we just saw is true in general, that if you take the product of 2 finite cyclic groups, they're going to be isomorphic to z sub the product of their orders if and only if the 2 moduli are relatively prime. So you can look back up in our examples and go, oh yeah. When n was 2 and m was 3, it ended up being z6. But when n was 2 and m was 4, it didn't work. And that's exactly why, is because the greatest common divisor of 2 and 4 is not 1. Okay, let's try to walk through this proof here. We'll do it in 2 halves. It's an if and only if proof. I'm going to start by assuming that the greatest common divisor of my 2 integers is 1. And I'm going to give a name to the order of the element 1, 1 in Zn cross Zm. I'm going to call its order k. So maybe I should remind you, it's written down here, but I'll remind you by writing it again, that k is the smallest positive integer such that when I add 1, 1 to itself k times, I get 0, 0, okay? Smallest positive integer that does that. All right. So if we take k and we add 1, 1 to itself k times, well, of course, we're going to get k comma k, and like we just said, k is the order, that gives us 0, 0. But to have a 0 in the first coordinate, that number would have to be divisible by n. The addition in that first coordinate is happening mod n, and the only way you're 0 is if n divides you. Likewise, to have a 0 in the second coordinate, you have to be divisible by m. The only way that second coordinate is 0. So k is the smallest integer that is divisible by both n and m. All right? And there's a name for such a thing. It's called the least common multiple of n and m. The smallest positive number that is a multiple of both n and m is called the least common multiple of n and m. And you can ask me about this in an office hour if you've never seen this fact, but to keep this video short, I'm just going to say it, that the least common multiple of 2 integers is always computed by taking their, or can be computed by taking their product and dividing it by their greatest common divisor. In our case, that greatest common divisor is a 1, and so our least common multiple is the product. When n and m are relatively prime, the smallest integer that's a multiple of both n and m is their product. That's what I'm saying. All right, so k is the least common multiple. We just said that the least common multiple is the product, so k is the product. That's the order of this group by your homework exercise. So our element 1, 1 is a generator, right? Its order is the size of the group. And if you found a generator, you got a cyclic group, and it's got to be isomorphic to ZNM because every cyclic group of order NM is isomorphic to ZNM. All right? So that's half our work. If the GCD of N and M is equal to 1, then our product group is cyclic. Cool. Second half of the proof, I'll write it in here. Maybe it'll make the notes easier to read later. It's going to be by contrapositive. It's going to be by contrapositive because I'm going to just flip it around and say, well, suppose that the greatest common divisor is bigger than 1. Greatest common divisors are never negative. So if they're not 1, or they're never 0 as well. So if they're not 1, they're bigger than 1. All right. So this time, let me denote by k the least common multiple of n and m. And again, by this fact that the least common multiple is the product divided by the greatest common divisor, if my greatest common divisor is bigger than 1, then the least common multiple is less than nm. Look at this fraction when I say that one more time. If the denominator of that fraction is bigger than 1, then the ratio is less than the numerator, right? Because it's a fraction. Or sorry, not the ratio. Yeah, the ratio is less than the numerator. Good. Okay. So if you take any element, this is going to be kind of similar to what we did up above. If you take any element in our product group and you add it to itself k times, well, you get ka times kb, but that's going to give you, I'll just use the same colors, that's going to give you a 0 in the first factor because k is divisible by n, right? K is the least common multiple of n and m, so that first factor is going to be 0, and it's going to give you a 0 in the second factor because k is also divisible by m. Yeah, so k, this number, which is less than n times m, kills everything in the sense that when I add any element to itself k times, I always get 0. So that means that no element has order nm. Every element has order less than nm, right? But nm is the order of the group, so no element can generate, so our group isn't cyclic. So by contrapositive, if this group is cyclic, then the GCD is equal to 1. All right, so I'm going to cut it there, and hopefully you'll watch this before class and ask me about it, and we can do some more examples. Thanks for listening.